Hello all, this is another walkthrough video, and this is for Unit 6, for the Unit 6 past paper from January 2023. It's not written anywhere, but it's January 2023. Right, let me switch this off. Okay, so question 1, we'll just jump straight in. So a student estimated the temperature of a Bunsen burner flame using the apparatus shown. So we see that there is a burner here, a flame, a steel screw held in the flame, a thermometer and water. Okay, so question 1. The student held a steel screw in the flame and then cooled it in a test tube of water. Identify one safety issue and how it might be dealt with. Okay, so the screw will get hot, obviously. So the screw will get hot. Okay, therefore, you need to use tongs to avoid burning your skin. Or hands, okay? I mean, obviously you cannot touch that thing or put in the flame, etc. So you need something to hold it, okay? So that's question A. Part B. The student stated the energy dissipated by the screw in cooling is equal to the energy gained by water in heating. And then the student measured the temperature increase for different masses of water. She recorded the following results, all right? So the mass of water and the temperature increase, okay? Criticize the recording of the results. Okay, so first of all, what are the units for this temperature? It's probably Celsius, but it's good to specify. So, okay, there are no units for the temperature increase, for T increase. Okay, that's one problem. We need to criticize. So we don't care about the scientific results. We care about the measurements themselves. There is another thing is that I noticed that this is 9.9, this is 16.6, but this is a whole number, 20, okay? And the same is observed for the temperature increase. So this is 37.5, but these two are whole numbers. So there is an inconsistency. So the other thing is that there is an inconsistency in the number of significant figures. Okay, no repeats recorded. That's another problem. And not enough data. Okay. Part 2. State one variable that should be controlled for this experiment. So the flame intensity, I mean, you need to have a constant flame, like the temperature should be constant. So one variable, so the flame intensity it should be constant between measurements, and the timing, the time for the heating. Let me use a clean page here. So I'm gonna move over here. So the time for the heating of the screw I do make an effort to make to have a better handwriting, so let me know in the comments if you notice any improvement, but it's really hard for me. Okay, and another thing you can say, okay, you can say one of these things, you don't need to write all three. I'm just writing it because this is I'm supposed to be a teacher. Okay, so and the other thing is the distance of the screw from the flame. distance of the screw from the plane. Okay, part 3. Show that the temperature of the Bunsen burner flame is about 1500 Celsius above the initial temperature of the water. And they give the mass of the screw, the specific heat capacity for steel and for water. And okay, so let's see. So okay, let me think about how to work this out, because I solved this test a couple of days ago. So if we use the specific heat capacity of the steel times the mass of the steel times 1500, okay, and remember that I think I mentioned it in my lessons. So delta theta, in general, when you work with temperature and liquids and gases and all those things, it's best to use kelvins, okay? But for temperature differences, you can use Celsius, okay? Because if you convert, because delta theta is simply theta final, so the final temperature minus the initial temperature, okay? So if you convert this to Kelvin, you're gonna add 273, and if you convert this one to Kelvin, you're also gonna add 273, so 273 minus 273 cancels. Therefore, it's okay to use Celsius, okay? That's the reason. Right, so if we multiply all this, we get 2589.3 joules, okay? And do they give us the mass of water? They do, okay? So we are gonna use, so for water, let's use seawater times mass of water times delta theta for all these 3 measurements. So we have measurement 1, 2, and 3. So actually, let me write it like, to make it more understandable, let me write it as follows. So times delta theta 1, delta theta 2, and delta theta 3. Okay, and actually, we also have to write, now that I think about it, we need to write M1, M2, M3, okay? Actually, okay, this is confusing, so let's write it all down. So seawater, seawater, seawater times, okay? So this is M1 delta theta 1, this is the pair M2 delta theta 2, and M3 delta theta 3. So if we use these values here, we find 65.7 joules with the first measurement. With the second, we find 2602.1 joules. And with the third, we find 2591.6 joules. So the temperature of steel is indeed about 1500 Celsius, okay? And this was question 1. Let's do question 2. A student used the apparatus shown to investigate circular motion, and they show the apparatus. The rubber band with mass m, this one, okay, was rotated around the plastic tube at a constant angular velocity omega. The part of the string between the rubber band and the plastic tube was almost horizontal. The mark on the string was kept level with the bottom of the plastic tube so that the length x stayed constant. The mass capital M provided the tension F in the string. Okay. The variables in this experiment are related by the formula mg equals mx omega squared. Show that the relationship between the period of rotation t and mass m can be written as that one. Okay, this is kind of easy. So mg is mx times omega, but omega is 2 pi over the period squared, right? So if we rearrange, we immediately find that t squared is simply 4 pi squared times mx over capital M G, and that's the answer. Okay. Part 2. The student used a stopwatch to determine t, the period, for different values of mass. Devise a plan to test the validity of the relationship between t squared and m. Okay, the method should use a suitable graph. Okay, so from this formula over here, we expect that t squared, if we plot it with respect to m, we should get something like this. Okay, and this is because this is the graph. This graph is the graph 1 over m. Okay, because this is the relationship between these two guys. Okay, so somehow we have to take measurements, enough measurements to make this plot. So first of all, okay, to do this experiment, you need to keep the length x constant. Okay, so that's the first requirement. You need to keep x constant. Okay, you need to use a marker to identify the start and the end of a rotation. Okay, you have to set the bank into rotation and start measuring after a few rotations. Okay, decide, that's the other thing, decide on a number of rotations measure the time needed, the time taken actually for the rotations, and divide by that number to find t. Okay, what else? Let's use a clean page. Take at least at least 5 measurements of t for 5 different masses, capital M, and this is the number 5. It looks like an S, but this is a 5. Okay, and then plot. Okay, here I plotted wait a second, let me think of something. Yeah, that's right. If you plot t squared versus the mass m, you're gonna find this graph. But if you plot t squared versus 1 over m, you should get a straight line. Okay, so this is what we will write as the last point. So plot t squared versus 1 over m. Okay, the gradient must be equal to this value over here. Okay, this value, 4 pi squared mx over g. 4 pi squared mx over g, okay? This was quite long, but this is what you have to do. For those of you who are wondering how this works, I recommend you actually do it, like find a straw and pass a thread through it and try to make this arrangement. Watch a YouTube video, someone must have done this before, something like that. But the idea is that the centripetal force, m, where m is the mass of the bang, times omega squared times x, should be equal to m times g, okay? So this is the tension from the string, and this tension is equal to this tension over here. So, sorry, the tension is equal to m times g, okay? And that's the idea. All right, wait, there is a part B. I almost skipped it. Okay. The students suggested that using a video recording of the motion would improve the determination of t. Comment on this suggestion. So this is an excellent idea, actually, because the video recording allows you to better judge when the my handwriting. I promised I was gonna make better letters. So it's gonna the video recording allows you to better judge when the rotation is complete, because you can pause it, you can take it back and forth. And now that I learned a little bit about editing, you know, you can open it, you can open a video in CapCut or some other video processing software. I think Apple iMovie does the same. And there are many tools out there. So you can open the video in a video processing software, and you can take it back and forth and determine when a complete rotation was done with a lot of accuracy. So the video recording allows you to better judge when the rotation is complete. Okay. Thus, t can be determined more accurately. Okay. All right. Let's go to question 3. A student investigated the damping of a rotational pendulum using the apparatus shown. I'm gonna pause here and comment on the fact that in this Unit 6 paper, and in general in many of the Unit 6 papers, things that you were not taught explicitly in Unit 4 or Unit 5 or Unit 1 and 2, whatever. So things will appear that you were not taught. I mean, this kind of thing, you don't learn it anywhere. But you shouldn't be scared, because usually these questions show you what you have to do, okay? So even if you don't know the theory or the physics behind some apparatus that they might have as a question, they will guide you through solving the problem, as in this case. So this is the apparatus. So I'm over here now. When the metal rod is rotated through an angle and released, the rod performs angular oscillations about the vertical axis through the wire. Okay, the plastic sheets dampen the oscillations as they move through the air. Okay, so these are the plastic. Okay, let's use a different color. So these are plastics. Okay, this and that. So you have to imagine these rotating this way, so back and forth. So the wire makes this thing undergo a rotational oscillation, okay? But it's damped in that there is an air resistance from these plastic sheets that eventually will make the oscillation die, okay? The relationship between the maximum displacement angle theta and number of oscillations n is given by theta equals theta naught e to the minus lambda n, where theta naught is the initial displacement angle and lambda is constant. So if we look at this thing from above, okay, this is the first plastic sheet, this is the second one. Actually, let me use blue like before, and they are connected. So if we're looking at this from above, there will be a motion that looks like this, okay? So something like this, and theta will be this angle, okay? And it will go back and forth between two extreme angles, and every time it oscillates, the more this angle will reduce according to this relationship, okay? So this is what's happening, and theta naught is the initial displacement, okay? So the maximum one, okay? This is quite involved. Okay, explain why a graph of ln of theta against n could be used to determine a value for lambda. See, this is an easy problem actually, despite the difficulty in this problem, in understanding what's going on. So theta is theta naught e to the minus lambda n. So if we take the ln of on both sides, we will find ln of theta is equal to ln of theta naught minus lambda n. So plotting ln of theta versus n produces a straight line with a gradient equal to minus lambda, okay? And that's the answer. And this will allow you, of course, to find lambda, okay? Because this has the form y equals c, okay, this is the constant, plus mx, where m is minus lambda, okay? Let's move on. Part B. The student displays the metal rod by a large angle. He recorded the maximum displacement event every 10 oscillations. Okay, question I. Plot a graph of ln of theta against n on the grid opposite. Use the additional column for your processed data. Okay, so we are given n and theta, so we have to calculate the ln of theta. Okay, so now that we have the values, let's try to plot it. So, okay, let me use there is a ruler tool, okay, I'm back. I drew all the points, and I'm trying to use these tools to draw the line. Okay, I found this ruler, and let's see, so this is the line, the best line, okay, let's draw it like that. Okay, great. So let's take the ruler away. Right, so this is the idea, and then if you draw this line, you can take any 2 points you want, okay, to calculate the slope. So from what I have in my notes, I took this point over there, and then this point over here. So this is 1.9, and this is minus 47, okay? I mean, from here to there. Actually, if we are here and we subtract 47, if we are here and we subtract 47, we come there. Okay, so let's go calculate the lambda. So lambda is 1.9 over minus 47. That's equal to, okay, it's minus of that, so 0.04 is the answer, okay? I made it a little bit harder, but all you have to do is to divide this with that, okay? And about the graph a little bit, okay, take advantage of this square here, this square or this square, etc. And it's good to have jumps of 10 for the n and jumps of 0.5 for the ln, okay? And it's okay if your graph does not start from 0, okay? That's important. All right. Part 3. The student claimed that the initial displacement angle was greater than 180 degrees. Deduce whether the claim is correct. So to find the initial angle, we need the y-intercept. So y-intercept is equal to the ln of theta naught. And from the graph, okay, we see that the ln of theta naught is about 5.25, which gives us that theta naught is, theta naught is e to the 5.25, which gives us 186.8. Actually, let me calculate it because it might be a little bit more. To the 5.25, okay. So 190.56 is actually what I find. Okay. Check the mark scheme. Maybe my calculation is not fully accurate. Okay, which is larger than 180. So the student is correct. So student is correct. Okay. Right. And I think this is the final question for, okay, yeah. So a student measured a metal ring of the type shown below. The student measured the distance d of the hole, the diameter d of the hole in the center of the metal ring with a set of digital calibers. Explain one technique one should use to deduce the uncertainty in the measurement of d. So we have to take, to avoid the random error pretty much. So take measurements at multiple orientations and calculate the mean. To eliminate or to minimize the random error. Okay, so when I say multiple orientations, I mean you can measure d this way, and then this way, and then this way. So multiple orientations. The way I drew this thing now, it looks like a spider to me. I don't know. Let me know in the comments what this reminds you of. So, okay, let's move to part 2. Okay, she recorded the following measurements, determine the mean value of d and its uncertainty in millimeters. Okay, so the mean value, is equal to, we have to add all of this together, so plus, and then divide by 4, because it's 4 measurements, and the answer is 854 millimeters. And then remember, when we are dealing with a series of measurements, like when we have multiple measurements, the uncertainty is found by the half range. So half range is equal to, okay, what's the range? The maximum value is 8.56 and the minimum value is 853. So minus 8.53 over 2 gives us 0.02 millimeters. So the mean value of d is 8.54 and the uncertainty is 0.02. Okay. And by the way, the number of significant digits here must match the number of significant digits there. Okay. B. The student was given a metal ring of a different size. She measured the distances shown. Okay, so that's the diameter of the inner ring of this part. Okay, the inner circle, the hole. And this is, and S is the diameter of the outer circle as we see it. So, okay. She calculated the shaded area A of the metal ring using the formula. Okay, that's correct. show that the uncertainty in d squared is about 1 squared millimeter. Okay, and we're given the d. Okay, so the percentage uncertainty, since we have to, okay, we have to find the uncertainty in d, okay, which is 2 times the percentage uncertainty of d squared. Okay, so the percentage uncertainty of d. So we have to calculate the percentage uncertainty of d, which is 0.06 over 10.7 times 100. That's 0.56%. Okay, so the percentage uncertainty in d squared is 2 times the percentage uncertainty in d, which is 1.12%. And to convert percentage uncertainties to absolute uncertainties, we have to do the following. The absolute uncertainty in d squared is equal to d squared itself times the percentage uncertainty in d squared. Okay, and if we do that, we find 1.28 squared millimeters, which is about 1 squared millimeter. Okay, so I will remind you here that if you have x squared, if you're measuring x squared and you want to find the absolute uncertainty in x squared, you have to find, actually, okay, x to the n, actually, okay. Will this work? It worked. Okay, x to the n, where n is some integer. Okay, so the percentage uncertainty in x to the n is n times the percentage uncertainty in x. Okay, and then the absolute uncertainty in x to the n, you have to multiply x to the n with its percentage uncertainty, and it will give you the absolute uncertainty. Okay, part 2. Show that the percentage uncertainty in A is about 0.4%. Okay, this is going to be a little bit more involved. Okay, we're given a squared, and we know that A is that. So the absolute, okay, so the absolute uncertainty in A is going to be pi over 4. Okay, because it's multiplied by a constant, so we multiply the absolute uncertainty by a constant if the quantity is multiplied by that constant. Okay, please watch my video in uncertainties. Actually, this is a good point to, this is the first time I think I am mentioning this, but I do have a video on uncertainties, so watch that, and hopefully it will help you understand what I'm doing here. So the absolute uncertainty in A, which is this thing, is equal to pi over 4 times the absolute uncertainty in S squared. But even though that's a minus there, we have to use plus, okay? Plus the absolute uncertainty in D squared, okay? So the absolute uncertainty in the area is 2.58 squared millimeters, where I used, I am using this for the absolute uncertainty in D squared, and for the absolute uncertainty of S squared, I'm using the quantity given to us, okay? Now, if we want to calculate the percentage uncertainty in A, we simply divide the absolute uncertainty in A over A times 100. So this is equal to, I'm going to use a clean page. Let me make sure that I am doing this correctly. Okay. Yes, that's correct. Okay, I'm sorry, I got myself confused a little bit. Okay, so the absolute uncertainty in A is 2.58, and then we do have to calculate A, which is pi over 4 times S squared, which is 881, minus 114.49, okay, and then multiply by 100, this gives you 0.42%, which is about equal to 0.4%. And that's the answer. The student measured the total mass M10 of 10 identical metal rings as 63 grams. Explain why measuring the total mass of 10 metal rings is better than measuring the mass of one metal ring. So the percentage uncertainty of the mass is equal to the absolute uncertainty of the mass over the mass itself times 100. Okay, so if you measure it one time, so in both cases, if we measure one mass or 10 masses, the absolute uncertainty will be the same. So absolute uncertainty is the same when we measure 1 or 10 rings, okay? But the mass of 10 rings is of course larger than one ring, okay? And let me use a clean page, okay? Thus, measuring 10 rings reduces the percentage uncertainty. Okay, and that's the answer. Part D, part 1, okay. She measured the total thickness x10 of a stack of these 10 metal rings. Determine the mean density ρ in grams per cubic centimeters of the metal the ring is made from. And we have the mass of 10 rings, the thickness of 10 rings, and the area. Okay, so let me think. Okay, so the density is pretty much equal to the mass of 10 rings over over the volume of 10 rings. Okay, over the volume of 10 rings. Okay, sorry, I got confused for a moment. So this is equal to M10 over the area of one ring times the thickness of 10 rings. Okay, and this is because 10 with 10 will cancel. Okay, you can equally divide this by 10 and divide this by 10, but it's the same because we are dividing m with x, therefore that factor of 10 goes away. I hope this makes sense. If it doesn't, ask me in the comments. Okay, so we are dividing 63, that's in grams, so that's good. But then we are dealing with millimeters. So let me remind you that 1 millimeter is 10 to the minus 1 centimeters. Okay, so okay, let me think. We have 602 times 1003, so grams per cubic millimeter. Okay, and this, let me use the clean page. This is 7.46 times 10 to the negative 3 grams per cubic millimeter, and then we have to convert to centimeters to the minus 3, centimeters to the 3, I'm sorry. So 1 millimeter is 10 to the minus 1 centimeters. Therefore, all you have to do is to write this, okay, the numerator is the same, and then we have to divide by 10 to the negative 3 centimeters to the negative 3, okay, and this is because 1 millimeter is 10 to the negative 1 centimeters, okay, so this 10 to the negative 3 goes away, and we find 7.46 grams per cubic centimeter, which is, actually they don't tell us what we are looking to find, but that makes sense, okay, I mean, this is a metallic thing, so it has some weight. Right. The density of stainless steel ranges from 7.48 grams per cubic centimeters to 7.95 grams per cubic centimeter. Deduce whether the metal rings could be made from stainless steel. Okay, in our case, what we calculated is a little bit less, so they are kind of asking us to find the uncertainty. Okay, so let's find the percentage uncertainty in rho is equal to the percentage, because we are dividing things. That's why when we are dividing things, we have to work with the percentage uncertainty of a quantity. So here we are dividing the mass of 10 rings over the area of one ring over the thickness of 10 rings. Okay, so this is equal to the percentage uncertainty of M10 plus the percentage uncertainty in the area plus the percentage uncertainty in X10. Okay, and this is equal to the percentage uncertainty in M10 is simply 0.5 over 63. Okay, so 0.5, which is the absolute uncertainty, over 63 times 100, plus for the area, we are actually given the 0.4%, so we will take advantage of that and use it, and then plus 0.04 over 1403 times 100, and this eventually yields 1.48%, which is about 1.5%. Okay, so I'm gonna go here. So rho that we calculated is 7.46 grams per cubic centimeters, plus or minus, let's use 1.5%. Okay, so if we multiply 1 by 0.5% with 7.46, we will find the absolute uncertainty, which is 7.46 grams per cubic centimeter, plus or minus 0.11 grams per cubic centimeter, which says that that the range, so rho ranges from 7.35 to 7.57. Okay, and with the values given here, it's indeed steel. Okay, so indeed the rings are made of steel, and that's the answer. Okay, and this was unit 6 from what did we say, from January 2023. I hope these videos are useful. If you run into trouble, or if there is something you don't understand or you don't like about these videos, let me know in the comments. And please like these videos, it helps with the algorithm. And see you in the next one.